All right. So yeah, I am going to give a sort of brief overview of quantum error correction and try to, since there's a rather diverse audience here, I want to kind of give a simple build-up to what kind of questions we might ask, what the hurdles might be for quantum error correction, as opposed to, for example, classical error correction, and a couple of pieces of terminology and definitions that may be helpful for understanding Jeongwan's talk afterward on Floquet codes, since they rely a little bit on a lot of different concepts. So with that, I probably don't need to motivate too aggressively here that hardware is subject to noise. So whether we're talking about a classical computer or a quantum computer, there's noise of various kinds. The type of noise is a little bit different between a quantum computer and a classical computer, but nonetheless, classical error correcting codes also exist. And we don't even necessarily need to think about computers to ask about classical error correcting codes. We could think even just about asking about like barcodes and QR codes, which are error correcting codes. And so there's, if we were talking about the classical memory here, think about bit flips and try to ask whether we can make our information less susceptible to damage under bit flip type of errors. And so then we want to go ahead and extend those kinds of questions to ask about quantum hardware. So whether it's superconducting qubits or an optical quantum computer, how can we develop a quantum error correcting code, both in theory and in practice, so that maybe we can kind of scale up a quantum computer reliably and do something rather non-classical with it, and do something maybe out of the scope of current classical computers. So to take it back, I'm just going to think about a classical example of what kind of error might happen and what we might try to combat this error. So if I think about Alice trying to send a 4-bit message to Bob, and let's say she wants to send 0001, and Bob receives 1001 due to a single bit flip error, we can ask, what can we do to try to make a single bit not be corrupted so easily? And so we can try to think about, okay, well, if I had 0, then I might try to do 00, and 1, I send 11 instead. So Alice will send 00 if she wants to send a 0, and for each 1, she'll send a 11 instead. And Bob will look at this pair, and maybe he looks at the parity and he says, if he sees that it's an even parity, then he knows at least he can say that, that this is definitely a message that Alice could have sent. But if he sees that it's odd parity, say for example 01 or 10, then Bob knows that there's some kind of corruption that has occurred. He can't really do anything about it, but he can at least go back and ask Alice to send another copy of it, because he is certain that there's some kind of corruption. So can we do a little bit better than this? So then we try 0 goes to 000, 1 goes to 111, and then now Bob might try to check the parity of neighboring pairs. So he might check the parity of the first 2 and the second 2. So here I've just gone through and enumerated the 8 possibilities that he could have received. And the parities here, so the first number is going to label the parity of the first 2 bits. The second number will label the parity of the second 2 bits. And so they're both even parity, so we get a 00. And likewise, if I look at the 111, we also get 00. And so we infer that there's no error. And then we could likewise go through and say, okay, these 2 have the same parity, this is even parity and this is odd parity, so you get 0, 1. And we can attribute this to being an error on the 3rd bit. And likewise, if we go through, we can see that essentially there's a one-to-one correspondence between the possible parities that we see and the errors or the single bit errors that we might map it to. So this means that if single bit errors are the only issue, so a single bit flip is what could have occurred, then we have a way to uniquely find out which one needs to be flipped. Of course, you might ask, oh, well, it's possible that more than 1 bit flipped. Indeed, if, for example, if I started with 000 and then the first 2 bits were flipped and I ended up in 110, then I would wrongly infer that the error is on the 3rd bit. and try to flip that. And then I would think that the message was 1 instead of 0. So indeed, it is possible still. However, the thought is that if the probability of a single bit flip is rather low, then the probability of 2-bit flips is going to be even lower. So at least at, we can think of it as that, like, being first order, this will be a reasonable error correcting code. So just to kind of summarize this scheme and introduce the terminology that we'll need for the quantum error correcting code, we can think of 000 and 111 as being the code words that Alice could have sent, which represent the logical, the two encodings of the logical bit. So 0 could be 000, 1 goes to 111. And the error correction was achieved by measuring the parity of the adjacent bits and seeing if any of them are odd parity, because the code words should have even parities only. And from this, we were able to determine that single bit flip errors could be corrected. So that there are some drawbacks to the scheme. So we already mentioned, okay, single bit flips are all that you can basically do. This is also not necessarily an optimal scheme in terms of sending the number of bits you have to send in order to communicate a certain number of logical bits. And indeed, there are many, many more codes that are more complicated, but that have come afterward, and many of these have actually been used. So there's this Golay code, which was from 1949, which was used on, I think, the Voyager spacecraft. And Reed-Solomon codes are also currently used, and there are many more than this, but this is just a kind of a short list of the ones in the classical error correcting world. So yeah, this kind of gives us a point to start for quantum error correcting code. So I want to first introduce a little bit of notation. So we'll basically only concern ourselves with qubits here. And for that, we will introduce the Pauli matrices. So sigma x, sigma y, sigma z, which I'll just abbreviate as x, y, and z, are defined using these three matrices here. And I guess hopefully that minus sign in the y is in the correct place. So suppose we want to encode one logical qubit, and we're going to basically take our scheme that we just discussed and try to promote this to a quantum one. And this labeling will I'll choose to just work in the z basis. So sorry, was there a question? No? Okay. So I'll use a notation here where this bar is indicating the logical qubit that I'm trying to encode, so the state of the logical qubit, and the unbarred numbers, or the unbarred indices here, will indicate the states of the physical qubits that are used to encode the logical qubit. And to promote my parity code from before to these operators, we can see that, for example, ZZI and IZZ could achieve the parity checks that were required from the previous example. And indeed, this will give us protection against single qubit X-type errors, because the code words here are +1 eigenstates of these two operators. So ZZI acting on either of these two states will leave it invariant, and IZZ will also leave them invariant. However, if I introduce an X-type error, let's say I go and act on one of these bits with sigma X, let's say I flip this one, and we know that one of these parity operators now will come in and measure a minus sign in front of it. So ZZI this will now be a minus eigenstate of ZZI. And likewise, if I go to IZZ, and let's say X had acted on the third bit, or third qubit, then we would be able to measure it there as well. So like this, we can promote the classical single bit flip code to a quantum code, at least as far as we're concerned with only single qubit X-type errors. But we should also be worried about the phase, because after all, this is a quantum bit that we're trying to encode. So we should be worried about both the bit and the phase. So we should also ask about, what do the logical operations on these qubits look like? So that is to say, I need some way to turn a 0 bar into a 1 bar. And so what is the operation on the physical qubits? What does that look like? So this is just defining what these operators should be, what their action should be on the basis states. And then we can find such operators that will achieve this for us. So it's simple enough. X bar is going to be x, 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 and x, x, x acting on 0, 0, 0 will give us 1, 1, 1. And down the road, I will suppress the O times in between the x's. So if you see this kind of thing, such as, in this bottom left here, I have an xxx, this really means a tensor product of x's. So we have a logical x. Now we ask, what is logical z? So logical z can be any single qubit z. If I did zii acting on 1, 1, 1, then I would pick up a minus sign. I could also do izi, I could do iiz. All of those will give me a minus sign out front, which doesn't bode well because it requires me to only act on a single qubit in order to change the phase of the encoded qubit. So can we find a better quantum code to achieve this for us? So this gives us a good jumping off point to study a more sophisticated code or a more sophisticated type of code. So this general type of code will be called stabilizer codes. And you can think about classical codes in this way as well. And so the setup will be as follows. We have k logical qubits that we want to encode in some n greater than k physical qubits. So in the previous example, we had a single logical qubit that we wanted to encode in 3 physical qubits. And we'll just denote the poly group on n qubits. So these are just all possible products of poly matrices on n qubits. We'll call this Pn, and we choose an abelian subgroup S of Pn. And we'll use this S to define a code space, namely that it's the space of all possible, all the quantum states, which are the mutual +1 eigenstate of all of the elements of this abelian subgroup. So in our example so far, we had that this group could be generated by ZZI and IZZ. So our states were then, we could then find a basis for C as 0, 0, 0 and 1, 1, 1. And the idea is that by measuring an independent set of these stabilizers, we obtain a syndrome, meaning this is the equivalent of this parity table that I drew up before, which we then basically use as you take to some lookup table and determine which qubit suffered from what kind of error, and then we would apply some operation to reverse it. So the last ingredient that we need here, or the second to last ingredient, is that a logical operator such as the one that I just described, so X bar and Z bar, is some element of the poly group which will map one element of the code space to another element of the code space. So for example, we found that XXX and ZII are valid logical operators for the encoding described before. And finally, there's a relationship between the number of independent stabilizers and the number of encoded qubits and the number of physical qubits. And this relationship can be described as k equals n minus m. So, for example, in the calculation that Jeongwan will show, well, hopefully, I think he will show later. He will show that if you take his code and you view it kind of on its as is, you'll actually find that it has no I guess static logical qubits encoded when you try to do this kind of analysis. So we'll actually carry out this analysis shortly for 2 more codes, just to see kind of how this all shakes out. So we can go to one non-trivial quantum code, and that non-trivial quantum code is the 5-qubit code. And so the generators of this code are enumerated here. There are 4 of them. So there's 5 qubits and there are 4 independent generators, XZZXI, IXZZX, and so on and so on. And we can first check that these are algebraically independent. So if I multiply any pairs of them, I'm not going to be able to make the other one. And so that's maybe a little bit harder to see, but I think if you sit and try it, you'll maybe be able to convince yourself of this. something a little bit easier to see is to just convince yourself that they do commute with each other, because although you can see that some of them have x's where other ones have z's, these always happen in pairs. So for example, if I look at the top two, this has a z on the fourth index and an x on the fourth index. So these two anti-commute, but then there's another pair of x and z like that on the second index. So it anti-commutes twice, and so the total operators commute. So this then tells us, okay, we have verified that they're independent and they commute. So now we can try to figure out what is the dimension of the code space. One way to think about this analysis is to think about how each stabilizer, since we require that our code spaces consists only of states which are +1 eigenstates of these operators, each of these operators is essentially going to divide the 5-qubit Hilbert space in half. So if I think about all 2 to the 5th states, then the first operator will partition it into 2 states that will either be the +1 or -1 eigenstate. And the next one, by being independent, it'll do it in a different way, but it will still partition them. And if I do this 5 times or 4 times, you'll basically get 2 to the 5th over 2 to the 4th, which will give you a dimension of 2, which is 1 logical qubit. So this tells us that using these 4 operators, we can encode 1 logical qubit. And we can identify a pair of logical operators, this x bar and z bar, as being x, 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 z, 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 z. And we can verify that these operators do indeed commute with these stabilizers. So again, for the reasons that I described, if you just go through and check the number of times that it anti-commutes with the, either z or x, you'll see that it's always an even number. And interestingly, these two anti-commute with each other as required, because they're supposed to be a representation of x bar and z bar, which should obey Pauli commutation relations. So the last piece is that these are also not in this, they're not generated by this set either. So these are elements of the Pauli group on 5 qubits that are not actually in the stabilizer group, but which commute with everything in the stabilizer group. And that's important because, for example, I could add one of these operators to this set, and then suddenly 2 to the 5th over 2 to the 4 would become 2 to the 5th over 2 to the 5th, which would give me 1, which would be 0 logical qubits. So you have to, have one out to at least have some logical qubits encoded. So now we can see that we have single qubit X errors and single qubit Z errors that can be corrected by measuring these operators. So indeed, if you go through and you look at what is the corresponding syndrome that would emerge from applying a single qubit X or a single qubit Z, you'll get an independent mapping like the one shown in the earlier slides that you can then use to determine which single qubit needs to be flipped and in which way. There's another rather famous example of an error correcting code that is also has great significance in the condensed matter community. And there's a wide variety of people in the audience here, so I want to try to explain what this model is in two ways. So this is both a code and also commonly thought of as being a Hamiltonian whose ground states are interesting, and it's defined as follows. So consider a square lattice with periodic boundary conditions, or otherwise being viewed as covering the surface of a torus. And the degrees of freedom will be qubits, and they will live on the edges of the square lattice. So these are denoted by these dots. And the stabilizer operators that we talked about before, those will now be generated as follows. So one of them will be this star type operator labeled V, which is a product of sigma X acting on its four neighbors. And this will be at every vertex. And similarly, we'll have a Floquet operator, which is a sigma Z acting on the 4 edges around every face. So we have this operator at every face, and we have this operator on every vertex. And commonly, the code space of this is thought of as being the ground state of this Hamiltonian, which is going to be minus of the sum of these star operators and minus the sum of the Floquet operators. And we can also view it as, instead thinking of it as, these are going to be stabilizers which we measure, and then conditioned on the syndrome that we measure, we then apply some error correction procedure. So we will go back and apply some X's and Z's in order to flip things. And so we can apply this analysis for counting states as we did before. We can apply it now and try to determine what we already kind of know probably is that there's four ground states, but let's try to do it this way as well and make sure we arrive at the same conclusion. So if I think about these stabilizers on the torus, I'll conclude that actually if I multiply all the X's together, all the stars together, I will get the identity. And similarly, if I multiply all the plaquettes together, I'll get the identity. And this tells us that there must be these two of these stabilizers cannot be or must be dependent on the others. So that means that if I look at the number of independent stabilizers, it's actually going to be n minus 2. And so that tells us the number of logical qubits is 2, which gives us a 4-fold ground state degeneracy.
Hey, Karthik, we're at 12:31, so that'll you can probably just flash the next couple slides. I think it's nice that we got to that. That's a
So this basically just tells us that gives us another way of thinking about the toric code. The final thing to maybe discuss about the toric code is what the logical operators look like. And these look like two strings, X going on the dual lattice like this, and Z going on the regular lattice, the original lattice, like this. And you can see that there's a pair of X and Z which anti-commute here. There's a pair of X and Z which anti-commute here. And so we get that these could be considered representations of two qubits worth of logical operators. It's a little bit tricky maybe if you've not seen this before to see that these indeed actually commute with all the stabilizers. So we'll just kind of briefly run through this because it also helps us see the other interesting feature of toric code, which is the emergence of quasi-particles. So if we think about X, if I apply X on one of these degrees of freedom, then since the plaquette terms nearby are products of Z's, they will flip in sign. So these two plaquette operators will pick up a sign. And let's say I did the same thing with Z, then the two star operators will pick up, would also pick up a sign. So I can do this over and over again where I just act in a string. I act X here and I kind of push the violation forward a little bit. And if I do this over and over again and wrap around the torus, you will eventually annihilate these two plaquettes, and that forms the logical operator. So there will be no violations left, and that tells you that the operation commutes with the stabilizers. And the final thing is that if we don't do this, we have one more interesting feature of toric code, which is that the endpoints may be viewed as quasi-particles, which are frequently labeled as E and M. So this is a reference to thinking about this as being like a magnetic flux, and this as being like a charge. So these operators as being charges. So these would be the E's and these would be the M's. And it turns out that these two quasi-particles have some non-trivial mutual statistics. And further than that, it is also true that, although I don't have time to kind of delve into this, but if you were to interchange E and M, these non-trivial statistics are, in a sense, invariant, or maybe you could say symmetric between the interchange of E and M. So with that, we'll move on to the main talk. So I'll introduce our speaker, who will talk about Floquet codes. He did his PhD at Caltech, advised by John Preskill. He was a Papalardo postdoc at MIT, and now is a principal researcher at Microsoft Quantum. So without further ado, Jeongwan, do you want to take it away?
Thank you.
Thanks, Karthik.
Thanks, Karthik. So I should share mine. Do you all see me okay, my slides? Yeah. So we are now going to talk about some of the recent developments in the fault tolerance scheme. Let me start with a brief remark why the fault tolerance is important. So you may hear all the news about the programmable quantum devices. There are experimental reports that says, oh, we can manipulate a certain quantum state, and we can apply an operation at will, and we can do it many, many times. So, oh, this is a signature that we can build a quantum computer eventually. But without demonstrating fault tolerance, the interpretation can be a bit weird. So the fidelity of the well, this is very schematic diagram. So the fully fiducial qubit or logical operation corresponds to fidelity 1, say. Then, but your quantum operation that you apply at your will is not perfect. So as you apply operation over and over again, the fidelity of your system goes down, 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 like that. And people, and if this slope is sufficiently small, I mean, if it is sufficiently close to this one line, this one straight horizontal line, then people get excited that we may be able to do something. But extrapolating this experiment, you will hit 0 point at some level. But then at that point, well, have we demonstrated that we can do the calculation indefinitely, or we just simulated that there is a noisy gate? So the focus has been pushing this curve, curve upward and upward. Eventually, we would hope to reach this horizontal line. But this line is too ambitious, and so we implement a certain software scheme that Karthik was introduced, that there is a specially designed protocol that we can look at some subspace of your full quantum device, and basically making this curve looks like this. So on average, everything looks just horizontal. Even the individual gates are degrading the full fidelity at some point. There's some feedback that you can do that boosts your fidelity some significantly. The burden of doing this jump, the error correction, is that this scheme, the fault tolerance scheme itself, is the major source of error. If you are building any foreseeable, well, in any reported architecture, the quantum error correction, the fault tolerance, implementation of the fault tolerance will occupy more than 99% of your all errors, just to find the errors. Okay, so let's step back and why we believe in the fault tolerance. There's a mathematical theorem which says there exists some positive number that applies for universally, such that for any quantum circuit you give me, if that circuit consists of, say, n gates, then I can transform some equivalent transformation to that circuit. You replace your quantum logic element to something else, and it will blow up your overall circuit by some multiplicative factor. But that multiplicative factor is pretty mild. It's going to be some polynomial in the log of n. Well, computer science literature, we often say polynomial when we really mean a power law. Keep that in mind. So there's a slight blow up in such a way that your overall circuit will be resilient to any kind of error as long as the per gate error rate is less than the pre-specified value. This value being positive is the key to this theorem. Of course, this theorem, well, as it is not really a theorem. And I am omitting a lot of definitions. I didn't define what a circuit is, what it means to be equivalent. I didn't define what the gates are, and I didn't define even what the fault tolerance means. But morally, this is the doctrine that we believe in. And in this polylog and factor, there are a lot of, well, this polylog factor, benignly looking, contains a lot of content in it. This polylog factor is meaningless if you don't define what the qubit is. You have to introduce what your qubit is in the first place. And then when you convert a given gate into a more fault tolerant gates, you have to specify what gates you're using. So there should be an elementary gate definition. And you have to specify how to implement each of those elementary gates in some fault tolerant way. And the error correcting code that we have just seen corresponds to only the identity gate. We have not discussed anything any interesting transformation on the code space. And the positive value actually depends on this fault tolerance scheme. So although the theorem says there is some universal value that applies for everything, but what is implicit is that you are fixing some fault tolerance scheme. And as a researcher, we have to think about all these factors together when you design a fault tolerance. And that's the challenging part. So I have to tell you what the mainstream ideas are. The mainstream, by far, is that people consider the surface code, the error correcting code that live on the square lattice, with the qubits living on the edges of that square lattice, and there's a check operator that is a product of 4 Pauli matrices. And then on top of that, that error correcting code serves as an identity gate. And then for non-trivial logical transformation, people do so-called lattice surgery. We will explain briefly what the lattice surgery is using a very simple example. And using only this, you can only do the Clifford transformation, which is classically efficiently simulable. To fully realize the universal quantum computation, you add in some non-Clifford gates, and there's a well-known technique how to do that. Why is it appealing? It has pretty high threshold in practical means. It's about like 1% or so, depending on the noise model, nature of noise model, of course, but the 1% at the gate level, then that's sufficient. And all the operation necessary to implement everything here is going to be local in two-dimensional architecture. You might not want to implement your quantum computer in a two-dimensional architecture, that's fine, but then you will have some other connectivity between your elementary degrees of freedom. And even in that case, you imagine your surface code as just a software, and you can implement software on your given architecture. And even in that scenario, it appears to be competitive. And there is the error correction part is very well understood. We have a very efficient decoding algorithms that works well, at least in simulation. Now, the surface code was invented by Kitaev 1997, I believe, maybe a little bit before than that. And it's now 2021, like 24 years after the invention. Still, we believe in that is the most promising code. What a disappointment. It's really challenging. All the studied, well, if you pick a random, well, say you randomly generate an error correcting code and you test its performance, it's not the design of that fault tolerance scheme doesn't end with picking up a code. You have to design the full circuitry to implement this. And at that circuit level, the pseudo threshold is not the threshold, but the true threshold is the number that appears in the fault tolerance theorem. The pseudo threshold is more practical thing. Your physical qubit has a certain error rate, and your logical qubit will have a certain error rate. And that your given implemented fixed size fault tolerance scheme will give you some function between the physical error rate and the logical error rate. And pseudo threshold is the point where the logical error rate becomes lower than the physical error rate. So this is the threshold that your very implemented, the finite size thing begin to help, above which it's useless. You are making your qubit worse.
So pseudo threshold is always above the actual threshold.
Yeah. So, but it's not mathematically well defined. You are comparing two different things. So your physical error rate there is in your logical error rate there, and it will have some relation, like something like this. And in a log graph, it will be a straight line somewhere like that. And if you naively do it, then you will have this is no fault tolerance. and this is with fault tolerance, and there should be some crossing point. But mathematically, it's not well defined because you're comparing orange to apples. This error rate is about the very physical degrees of freedom. This is about your logical qubit, which is not strictly comparable. But roughly speaking, this is the pseudo threshold. Pseudo. And yeah, if you pick a random error correcting code and implement it fully, then this value sits around something like 10 to the minus 5, plus minus 1 or 2 in the exponent. This is, unheard of error rate in any physical platform. So that's the challenge. And once you achieve that error level in some way, then going further down using surface code is extremely cheap. What you do is you just triple or quadruple your code distance, and that's it. That will blow up your spacetime overhead, but that multiplier is going to be something less than 100. So is there any error correcting code that brings you from 10 to the minus 5 to 10 to the minus 15 using 100 qubit step? I mean, the unit of in space time? I don't know any. So this is the why surface code, after all those years, survives as a mainstream error correction. So I've heard this quote somewhere, but I don't remember that. When veterans say something should be possible, then you should be able to do it. When they say it's not possible, well, it's just that they didn't do nothing very much. So we shouldn't lose our optimism, and there should be something better than the surface code, I believe. And here's another proposal along that direction. So let me get into the very definition. Extremely simple. Still identity gate, nothing more fancier than that, just identity gate, but here's the protocol. There are qubits on the vertex of your honeycomb lattice, 1 qubit. And for the sake of simplicity, let's put the periodic boundary condition. It's not absolutely necessary, and we will relax this later, but for the sake of understanding, let's do that. And we associate operators depending on the orientation. Say, well, yeah, this is the orientation specification diagram. For the positive slope edge, I assign an operator XX. This doesn't mean that I do anything with that. I'm just associating an operator with those. And on the horizontal edge, there is a ZZ. And for the negative slope edge, there is a Y and Y. And I labeled each honeycomb using 1, 0, 1, 2, so that the neighboring hexagons do not share the same label. And yeah, so I 3-color entire lattice. And the protocol is that you measure every edge that connects 0 and 0 pocket in the first round. So in this case, XX here, and YY there, and ZZ there. It's a 2-qubit operation, so you should be able to do this. And on the next round, you measure the edges that connect 1 pocket together. So like, let me try here. The edges that connect 1 pocket like that. And then the next round, you measure edges that connect 2 pockets, like this one, like that. And you repeat. That's it. No unitary gates, no CNOTs, just 2-qubit measurements, nothing else. Okay. So let's analyze this as a conventional code, as if it were a conventional code. In the conventional code, what do you do? When you say you measure a certain operator, you include that in your stabilizer group or subsystem group, and then you try to find some static subspace inside it. I think this word was not covered, but it is a variant of the usual stabilizer code, but you do not impose the commutativity. You do no longer require that your group is abelian. Well, how would you measure anticommuting operators? Well, you don't. The trick is that there is a people denote it gauge group, although the terminology may be debatable by physicists. People call it gauge group generated by all the check operators you want to consider. And then, oops, this gauge group contains some abelian group. People call it stabilizer group for good reason. So the gauge group is designed so that there is some non-trivial center. And this center will divide your Hilbert space into several pieces, many pieces. And in one sector, this is the place we want to put our logical qubit in, but we don't use all the subspace here. We further divide this subspace and use some part of it. If your subspace, for example, contained like 10 qubits, well, forget about 8 qubits worth. I'm just focusing on a 2 qubit worth of subsystem. It's no more a subspace because it is a subsystem of a subspace. That's why people call it subsystem code rather than a stabilizer code. But it's morally the similar thing. Now, the logical operator in this subsystem code is one that commutes with all the operators that you begin with. In that case, the subspace is preserved. You are discarding this garbage subsystem, so it's okay. And you hope that your operator is implementing something non-trivial on your subsystem within that subspace. So you can do the calculation by elementary bitwise operation. I mean, it's all Z2 calculation. There's nothing fancier than that. And after that, you realize that my check operator, according to my prescribed protocol, does not encode anything. There's no subspace that's interesting. So there is a non-trivial stabilizer group, but stabilizer group is too big to leave nothing for your logical qubit. I can skip how the calculation goes. Let me just proceed. So my protocol, in a conventional sense, does not do anything good. However, there's something in the dynamics. So for that purpose, I want to focus on the instantaneous stabilizer group. What is preserving my subspace at a given moment? So for that, I want to remind you with the dynamics of measurements. If you start with some state that is preserved, that is fixed by some stabilizer group, so let G be the stabilizer, and if you are starting with some state such that it is preserved by every element in your stabilizer group. Now, I want to project this state into another state. And here projector is going to be some measurement using some other operator, say P. Okay, the eigenvalue plus or minus 1, this sign will be determined by the actual measurement itself. You cannot predict what it will be in general. And there are a few cases. The operator that you are measuring could be already in your stabilizer group, in which case you will get a definite outcome, of course, in the absence of error. It may not be the case. It may be both of P and minus P resides outside your stabilizer group. And then you have to consider two cases. The first case is when the operator you're measuring commits with every element in your stabilizer group or not. There is some element in your stabilizer group that does not commute with your observable. In this case, your stabilizer group just enlarges. S becomes S and P, and plus minus the value will be equally likely. If it does not commute with some elements of it, then you have to subdivide your stabilizer group into two pieces, one that anti-commutes with your observable and another piece that commutes with it. You can always do that. Then your evolution, the post measurement will be just P up to some sign and the remaining commuting ones. This is the evolution rule when you measure a new operator given a stabilizer state. So applying this rule sequentially to our dynamics, well, let's start with the completely unknown state. So my stabilizer is just identity. And then I measure the check operators associated with the edges connecting 0 Floquets. Then trivially, I will be left with those. And the next step, probably this is the most complicated calculation, so let's do it. So initially, we get this situation. Look at this 2 Floquet here. We initially had these 3 operators that takes a certain eigenvalue in your state. The next round, what you do is you're going to measure the one. Let me change the color. Yeah, you're going to measure this operator and that operator. But in our design, every 2 check operators that are meeting at an edge anti-commute. So this red one cannot survive in the stabilizer group in the next round. However, this red operator times that operator will commute with my new measurement, so that will survive. And similarly for here, so the product of all 3 red ones will survive. So that gives us some operator associated with this hexagon and extra elements associated with the edges that connects one Floquets. And you just keep doing, and you realize that after 3 rounds, well, actually 4, 1, 2, 3, 4. After 4 rounds, there are some operator that is perpetual under the dynamics associated with each hexagon, and some operator associated with the edges, but they keep changing. This is going to be our stabilizer. I mean, this is going to be the one that remains invariant. We like something invariant. Because that's static. It's easier to deal with. Now, using that perpetual stabilizer, we can analyze what the state is. And the answer is that it is going to be isomorphic to the toric code, but living in some other lattice. So the gray lattice here is the original hexagonal lattice with the qubits. And at the round 0, at round 0, we are projecting these 2 qubits using one Pauli measurement. So we got 2 qubits worth of Hilbert space, but divided by one stabilizer, one check operator. So effectively, you're left with 1 qubit worth of Hilbert space down there. So I want to draw that effective qubit as an edge that penetrates, well, that is orthogonal to the given edge. And the result is that some larger super lattice that is happened to be also a honeycomb lattice. And in that honeycomb lattice, we get the perpetual stabilizer associated with each small hexagon. And those small hexagon turns out to act exactly the same as if you had the toric code on the super lattice. Remember, on the toric code, if you have like a super hexagonal lattice, then there are qubits on edges, and you get the product of z's around its Floquet, and every vertex you got the product of x around it. And by a judicious choice of z and x within this effective qubit, you realize that the perpetual stabilizer exactly corresponds to, if it is sitting at this super vertex, then it becomes like x. If it is sitting at the super hexagon like this, then it corresponds to the product of z. So at every moment, after sufficiently many initialization steps, you always have the embedded toric code. But due to the dynamics, the embedded toric code doesn't stay there. It keeps evolving. And here's an interesting aspect that Karthik was alluded. In the toric code, well, we heard the word quasi-particle. Physicists should be familiar with that terminology. For other backgrounds, I would say it is a it is a syndrome bit. I mean, there's some information that you can tell that there's some error, but this bit cannot be sent away cannot be removed by correcting some local error. Yeah.
Can I actually ask one general question at this stage?
Sure.
Is there a kind of general expectation that the k-locality of a code can always be reduced at the expense of like a time trade-off? That like here you're effectively reducing the k-locality required to do the toric code, but there's a time trade-off because now you have a Floquet cycle. You sort of generally expect that's always possible, or it has to do with the particular, like the code needs to have some automorphisms or something like that, like you're about to describe.
Okay, so you're asking an advanced question that I was going to tell you at the end of the talk. I don't know. It's an open question and it's very interesting. I believe this is going to be a prototype for investing in those kind of questions. And I'm really curious, what's the criteria for the dynamics to induce such an interesting dynamics on the effective level? Well, as a matter of fact, the automorphism that I'm going to talk about is discovered after we specify the dynamics. We didn't demand it. Yeah. Okay, so let's compare. This is round that is 0 mod 3, and this is round 0 that is 1 mod 3. And we have to compare two embedded toric codes at each stage. And the comparison, well, how can we compare that? We have to keep track of where the logical operator is evolving. But what does that mean? One logical operator that was acting here should be connected to another logical operator at the next round. But how can I determine the relationship? The requirement, actually this requirement is sufficiently strong to determine this. The requirement is that you imagine your initial state was a eigenstate of your logical operator. In this diagram, I draw one specific logical operator along this line. And you imagine that, yeah, this was the underlying state was an eigenstate of this. Now, in other words, this logical operator itself is a stabilizer, instantaneous group. And then you apply the evolution rule for your measurement dynamics to keep track of where the instantaneous stabilizer group evolves. And you try to identify the corresponding generator associated with this logical operator. In a more microscopic way, you find a representative of the logical operator in such a way that it commutes with every check in both rounds. Then you can find another instance of the logical operator that is depicted in this way, and you interpret the calculation result against the embedded toric code on the superlattice. You may wonder, oh, that's too microscopic calculation. There should be some general argument that this is happening. I don't have any good answer. That's also a question one should address. So the conclusion from this calculation, although very microscopic but well defined, you can even let your computer to do it, is that the logical operator that would have flipped the Floquet terms, in this case here and here, say, if you truncate your logical operator, then the perpetual stabilizer here and another perpetual stabilizer there would have anticommuted. Oh, there was a question. Yeah. That same logical operator evolves to one that flips now the vertex terms at the superlattice. The Floquet term was termed as an E particle in the topological phase literature, and the vertex excitation, vertex syndrome associated with the vertex term is traditionally called the E particle. And the one that was transporting this M is now transporting E on the next round. And this correspondence is the only non-trivial automorphism of the underlying Enian theory of the embedded toric code. And that non-trivial automorphism is realized by our purely measurement dynamics. And is this calculation robust? I have calculated this instance using a special one representative. And is this, well, what if I chose another representative logical operator? Well, remember that in the quantum error correcting code, it is essential for the logical operators to have many different representatives. That's actually equivalent to your capability of error correction. And so one representative calculation doesn't immediately say it is robust conclusion. But in this case, it is robust because any other representative is going to be connected by a stabilizer that transports the same type, and that doesn't change. So by calling it E and M, we're already modeling out all the possible representative ambiguity. So we're okay there. Now let's go to the more fault tolerance aspect, a little bit deeper into the fault tolerance. Let's step back. Let's consider the most general case in your error correction. There, people tend to think about the Tanner graph. Tanner graph is a bipartite graph. By the way, graph here means a node and their connection edges. So on the one, bipartite means that the nodes are partitioned into two categories. In one category, the nodes represent bits. Or for us, it's qubits. Or for more properly, they correspond to type of elementary errors. On the other category, you get the syndrome bits. Syndrome bits are those that when they are 0, you are confident that your code has no error, but when they are not, you have something to do. It signals that your qubits are damaged, so you have to do something. And as a code designer, you are already given this graph where the edge means that if this error occurs, then this syndrome bit will be signaled, will be flipped. And this syndrome bit can be flipped by this much errors, and this error will flip that much syndrome bits. So this bipartite graph encodes the information about how to decode. The decoding task is that you read this part, and then you identify what caused this syndrome bit. Well, this is not, in general, very hard problem. You can actually encode any NP-complete problem into this form, into this format. So don't expect to solve this problem in full generality. But for specific instances, there are efficient algorithms, and and we have to construct what this Tanner graph would look like before we tackle how to decode. So what are the syndrome bits? The syndrome bits are associated with the perpetual stabilizers. That's the something static is what we rely on, although the dynamics is periodic. So the perpetual stabilizers are there, but we know it's there, but we don't get to access to it through our measurement. Our measurement is just a 2-qubit checks. You know, in the first round, we measure that. And in the second round, we measure that, and so on. And only if you completed those 2 steps, you can infer the value of this perpetual stabilizer. And that should be our syndrome bit. So that. But observe that, you know, this syndrome bit is inferred only if you measure the 0th edge and then 1 edge. And at that point, you're only inferring syndrome bits associated with the type 2 plaquettes and nothing else. You know there's some operator that is preserved under your dynamics, but you don't get to look at it yet. You have to wait. So if the round goes like 1, 0, 1, 2, 0, 1, 2, and so on, from that stage, you infer type 2. At those stages, you infer type 0. In that stage, type 1, and so on. So every round, you read 1/3 of all plaquette stabilizers, and only the history will tell you whether you have errors or error or not. One peculiarity or special feature of this Floquet code is that unlike usual stabilizer code or any typical error correcting code, if your code space is here and you are hit by some error there, then you should be able to tell there is an error repeatedly, indefinitely. You know, unless you correct it, your check operator will keep reporting, oh, there's an error, there's an error, there's an error, that you and then you get confident. Here, even if some errors are hitting your system, they're gone after a certain period. One that is very special. Well, one where that phenomena is visible is error by the check operator themselves. If I hit my system by this operator that has happened to be equal to my operator that I'm going to measure, then at some point your perpetual stabilizer will be flipped around it. But as soon as you measure that, the same operator, the effect of your errors will be absorbed to the measurement outcome, and you no longer have any information about that error anymore. So that's a special feature. This is quite similar to usual measurement type errors. So in the design of error correcting code, you assume certain things are reliable. What you think reliable is probably your measurement outcome, but in reality, you shouldn't believe that. Even if your device says, "Oh, this is 0," well, I should think that there's some chance that it may have been 1. And in those measurement errors, if I repeat it, then, well, if your measurement device is sufficiently reliable, then those erroneous measurement outcomes will occupy a small fraction of it. Then you will have a more confidence in your measurement outcome. So measurement outcomes, even if it happens at some point, the relevant syndrome bits that are affected by this faulty measurement outcome is localized in space-time. Here in the Floquet code, not only those measurement errors are short-lived, but some poly error that actually damages your qubit can be short-lived. So to better understand the situation, we need to simplify our error model. And one simplification is the following. We assume that there is no measurement error. It's our assumption, not reality. And moreover, even if the poly error occurs, we may assume that the poly error can only occur if your measurement was like, if your measurement was by Z and Z at this location, for example, then I assume that the only error that can occur post this measurement, immediately after this measurement, is just Z, nothing else. And that is justified because you can generate all the other error configuration under this error model by blowing up some, by introducing extra errors in other locations. So you can generate, you are guaranteed to have a generating set of all errors. So it suffices to consider this simplified error model, at least as a theorist. So the decoding goes as follows. You keep measuring, and every time you measure type 0, 1, 2, and well, you keep doing this, then you infer 1/3 of the Floquet at a time. Yeah, so this is time step 0. And then at the next round, oops. You will be measuring those. So that's time step, say 1. And then the next round, you will be inferring those. So if I look at the space-time configuration of what bits are I have inferred, it will form a lattice like this. So in a further simplified diagram, it will look like something like this. So the time direction is going to be the 1, 1, 1 direction of this simple cubic lattice. So unlike any other code, well, the usual surface code or toric code decoding algorithm, the decoding graph happens to be the square lattice with the 0, 0, 1 direction being the time, the third direction. So we can draw the simple cubic lattice. But here, it is now rotated and Schur transformed. And you can do the usual decoding algorithm designed for the toric code, and you can migrate it into this decoding algorithm. Since I am running most of the time, let me go to this part. So far we have discussed the torus version of the Floquet code, and it's difficult unless you have a long-range interaction in your quantum device to implement this torus geometry on a plane. We need to find a way to introduce boundaries, but there's a dilemma. Every time you measure a new round, the embedded toric code interchanges between the E and M particle, and having a boundary in the toric code corresponds to condensing one of the particles in a condensed matter language. So we have to cope this order 2 automorphism with our periodic boundary condition, but our dynamical period is 3, an odd number, whereas the automorphism is 2. They are co-prime. So the usual strategy shouldn't work. You cannot keep the period at 3 exactly while having a meaningful boundary in this error correcting code. So the trick is that we enlarge the period of the dynamics and make it into 6 dynamics. So the original measurement sequence was to measure type 0, 1, and 2 edges, and then you keep going on. But here, you don't do that. You do this, and you repeat. This is period 6, and this is denoted as a arrow like this. And being a period 6, you have a good chance of coping with the order 2 automorphism of the underlying toric code, embedded toric code. And special treatment is given to this distinguished around 0, where we measure or not measure certain edges, and not measuring something happens to be sufficient to implement the order 2 automorphism in a conforming way. I thought I would have time to go to the entire architecture, but let me briefly sketch that. So, well, this is just a review of the usual strategy, how to build a quantum computer, starting with the surface code-like architecture. And the Floquet code, although it is conceptually different, but it is very similar to the usual surface code architecture. So let me briefly tell you how it goes. So one patch of your quantum device will encode 1 qubit, 1 logical qubit, and there will be a lot of them in a 2-dimensional plane. And then using a technique called lattice surgery, you can implement a joint measurement between neighboring patches. You can measure the product of 2 logical operators, Z and Z, without revealing individual eigenvalue. That's important. You should not look into the 1 qubit. And you can measure those as a product of operators, and that allows us to teleport logical qubit embedded. And teleportation means that I can move around my logical qubit anywhere into my system. So layout problem is now addressed. And then you have to implement the logical Hadamard or logical phase gate. Logical Hadamard is going to be implemented by a special trick that involves 4 patches at a time. And you rotate a certain logical operator into the horizontal form, and you make a lattice surgery to measure them. And the S gate is going to be supplied by the usual injection trick. But let me mention that just that there exists such a technique. So once you completed the Clifford, all the Clifford operation, then you bring in other magic states that is fabricated or distilled from other space in your, from other part of your quantum chip, and you teleport this distilled T state, and you inject to enact the so-called T gate. And altogether, this benignly looking elementary gate set implements all possible quantum operation up to polylogarithmic overhead, which is well understood. So you can build, in principle, a full quantum computer out of the Floquet code. So let me summarize. The main message here, by giving you an example, is that pure measurement dynamics, no unitary gate, no single qubit measurement, just a 2 qubit measurement, pure measurement dynamics can give a logical qubit, even if that logical qubit may not be found in any traditional viewpoint. The one interesting aspect of that is your logical qubit may be completely useless if you lost your history of measurement outcomes. The logical operator in my Floquet code is keep evolving according to the measurement outcomes that are implemented along the way. And if you just wipe all the measurement outcomes off in some time window, then you lose your logical qubit. Well, even if it's a fault tolerant, I mean, losing a couple of, well, some few randomly distributed measurement outcomes, that's fine, but you should not lose the entire time window. That's very important. And this particular code may be most likely useful with when your quantum device comes with the measurement as a primitive rather than unitary gates. And maybe physically most interesting feature is that it constantly implements the E interchanging M automorphism at every measurement round. And obviously, this generalizes to other 3-color graphs of degree 3. So I put some important looking questions, and here it goes. So it became now apparent. Traditional error correcting code design or fault tolerant scheme starts with selecting an error correcting code, and then you think about how to implement it in a fault tolerant way. Well, in this dynamically generated logical qubits, that approach has to be modified. Your entire circuit in space-time is now defining a logical qubit. We have merged two steps together. But this is one example, and we have not developed any general theory around it. So the obvious question, and I think it's an important question, is how can we tell if the circuit gives a logical qubit that is sufficiently fault tolerant? We do not have any criteria. For usual error correcting code, we know what to search over. I mean, we have to look at the code distance, but what is the corresponding thing here? Do we always have to look into the decoding graph? Well, that alone is already a challenge because we don't a priori know what the syndrome bit should be, and we don't know how to construct a decoding graph in general. And more generally, if such a criterion is developed, then we may be able to search over such a protocols. And maybe more physically ensuing questions are, when does the underlying state correspond to some topological ordered state? We used a Pauli measurement, so it may be the toric code embedded is the only choice, but what about the other possibility? And will automorphisms of the underlying MU theory emerge by this measurement dynamics? If so, in what circumstances they are? Well, this is what Mike was asking before. But I think that's an interesting question. Yeah, let me stop here. Thanks.
All right, thank you, Jeongwan, for the nice talk. And I guess, yeah, if people want to do the clap emoji or whatever that is, go for it. Now, I guess we'll open the floor for questions from anyone. This is, I guess, the period where we still have professors. So I guess professors, if you want to ask first.
I have a question.
Yes.
So I'm kind of curious about this history requirement here. So, you know, if you actually had a large machine like this, it sounds like there would need to be a lot of local classical state that was maintained. Or what's your thought about sort of the control aspect of this classical, you know, control aspect of implementing this? And would that be an issue if you had to do that at really cold temperatures or something?
Yeah, it is an issue. Yeah, depending on the circumstances, it may be a serious issue. So we need to take into account of the time scale at which your funnel operations may operate. So the classical computing, well, if we need like a 10 to the 15 operations in total to achieve certain non-trivial algorithm, then that each element has to be reasonably fast. Otherwise, we would have to wait thousands of years. And you know, that's a logical operation, and one logical operation amounts to, well, maybe order 100,000 operation elementary if you're accounting for all the electronics and you know, underlying degrees of freedom. And that has to be communicated with the very low temperature if your device is at low temperature. So, and the whole point of fault tolerance is to keep up with the rate at which errors are accumulating. You have to fight back sufficiently fast. So your bandwidth down to that bridge has to be sufficiently fast, and that may become a serious challenge. Yeah.
Well, in particular, I think I was going off of the notion that you have all these measurements that are going on continuously, and you need to keep that around in order to even interpret your logical qubits.
Ah.
And so it seems to me that bandwidth out of the cold isn't even possible here. Potentially, it's your classical control that's, you know, next to the qubits needs to be storing a lot of classical information and manipulating it on the fly.
So that's there's a one important aspect when it comes to Pauli type manipulations. So all we do, you know, in any of the Pauli based error correcting scheme, including stabilizer code or this purely measurement based Floquet code, the measurement outcomes doesn't have to be feedback to the device. That's non-trivial. I mean, the trick here is that you only keep track of which axis you are measuring into, and that information can be interpreted externally post-measurement. So all you have to do is you pump out all the measurement outcomes to the outside, and you don't worry about how to react against, you know, based on that. Exception is the non-Clifford gates. There you have to wait. And I don't see any other way, any way around it. But the one fortunate thing, well, it's a bad thing and good thing back and forth. One good thing is that wait happens at a logical time scale, not at the individual physical operation scale. So there's a hope.
I see.
Go ahead, Yimu.
Hi, Jeongwan. Thanks for the nice talk. I want to, you mentioned the necessity of keeping the measurement record. I wonder if you don't keep, if you just throw away the measurement record during the process, is that the same as measurement error? Does it mean there exists a threshold in the amount of measurement record that you can throw away?
So yeah, I want to, well, there's a fine line. So imagine the vertical line is time window and this is my space, then you can lose randomly distributed measurement errors up to some threshold, that's fine. What you shouldn't do is that you lose entire time window, everything in this time window. Then, yeah, and the probability that your, so the logical operator can depend on the measurement outcomes that resides in a certain membrane of 2 dimensions, and the chance that random errors are blocking every possible membrane is exponentially small.
I see. Thanks. It's like a percolation picture. Thanks.
Yes.
So I guess this is a little bit still on the same kind of question as Mike, but so if you have, so in this case, there was the toric code theory that came up, and it alternates between essentially swapping E and M.
Yep.
So this is the automorphism. Is this a necessary requirement? So for example, I guess the closest thing that I might think that is a little bit different but might emerge is like if I thought about like a double semyon kind of model. Would this do you think this could also emerge, and what is the effect of having something where
right, so yeah, it's all in the questionable area, I mean problematic area. We did not demand it, you know, that's for sure. Well, life could have been easier or not, you know, if we didn't have that automorphism implemented every round. And that's why we had to increase the period from 3 to 6 to combat with that. for other situations, some measurement dynamics may, yeah, it's hard to say. One hint is that the certain products of the check operators are a logical operator, and in this dynamical situation, that logical operator seems to have non-trivial self-statistics. In the very case, it is just a fermion. So, and that being a fermion sounds like, you know, you're adding, well, adding quote unquote, adding a fermion to E particle every time, and to M particle as well, and that's why E and M are interchanged. Similar thing may happen in other situation, but it's hard to say if there is any criteria.
Thanks. Anyone else want to ask a question or get some clarification?
Hey, yeah, thanks for the very nice talk. Is there a sense in which requiring these long measurement histories for the 2D code is related to how in 3D you can have actual stable quantum memory? Or do you not see any sort of connection between those two?
Wait, can you repeat the question?
Oh, sorry. The question is just here you have sort of a 2+1 dimensional code,
Yeah.
and whether this is related in a meaningful sense to just sort of static 3D codes.
Oh, well, excellent question. Right. Well, you mentioned that the whether there, well, the requirement that we need a long history of measurement outcomes, is that somehow related to self-correction in 3D? I mean, the dynamic versus static one. Well, that analogy doesn't always true. It's not always true, because in the usual Turing code implementation, we don't need the long history of measurement outcomes. You may lose some of the measurement outcomes in a time window, and that's fine still, because you know that every stabilizer, the logical operator stays invariant, basically. So that alone, the requirement that measurement history is required cannot be the reason that there's any connection to the static 3D. Now, can you convert any scheme that is fault tolerant in 2+1 dimensions to a static, some Hamiltonian scheme in purely 3D spatial dimensions? First of all, the 2+1 fault tolerance is not purely local in 2+1 dimensions. You need to post-process the outcomes inscribed in the 2+1 dimensional history, and you have to mix and match. And that classical processing loses locality. If you could decode this three-dimensional decoding graph using local rules, then the situation may be different. But it's I don't think I know anything like that. In even higher dimensions, it's possible. But in pure 3D, I don't think there's anything now. Even I mean, well, the decoding algorithm implementing in a fashion of some local Lindebladian, that may be too much to ask for. But even in terms of cellular automata, I think strict 3-dimension is still open, I think.
All right, thank you.
Anyone else? suppose we can maybe proceed to the, I guess, the nominal second phase of the, or third, fourth, whatever number phase of the colloquium, and ask the professors if there are any left